Welcome to Season 2 of Escape Velocity Space News. We're super proud of our show and really glad to be here to bring you more science, more spacecraft, and more technology news. Our season, like the life of an academic or a student, weaves itself through the school year, and we currently have a 22-episode season in the works. In the coming 8 weeks alone, we're looking forward to the launch of the Psyche Asteroid Explorer, the return of the OSIRIS-REx sample from the asteroid Bennu, and an annular eclipse of the sun that will be visible to roughly 1/3 of the United States. Making all of this possible is you. We release our shows under a Creative Commons Attribution license, which means you can take our content and share it, air it, and play it wherever you want. Just don't change it or forget to give us attribution. In order to keep our content free for everyone, we do have ads, but most of our funding actually comes from the generous contributions of people like you, most of whom don't like ads. If you like to enjoy this show ad-free, join our Patreon community at patreon.com/CosmoQuestX. In addition to ad-free videos and podcasts, you'll also get early access and bonus features. I hate fundraising, and if enough people join our Patreon, I'll never have to fundraise again. Goals, people, goals. Anyways, in today's episode, we look at the upcoming solar max, how solar activity affects Neptune, the robotic invasion fleet on Mars, and how some of the weirdest star systems in reality have been able to form. In our closer look, we fail to see dark matter, like everyone, but observe its gravitational impact on light from objects we can see. I am your host, Dr. Pamela Gay, and I am here to put science in your brain. In the next couple of years, we'll be talking more and more about our sun's 11-year magnetic cycle as we get closer and closer to its July 2025 predicted maximum activity. Here on Earth, this cycle will drive increased auroral activity, occasional radio communications outages, and inevitably, a few satellites will die early as solar activity expands our atmosphere into a satellite-consuming beast. It's thought some weather effects may also be related to the solar cycle, but in general, the weather is so chaotic and our atmosphere is being affected so much by human causes that it is often hard to tease out exactly how all the pieces fit together. Surprisingly, other worlds may offer a better look at what the sun is capable of doing. Since its launch in 1990, the Hubble Space Telescope has been taking regular images of our solar system's icy and gassy outer worlds. When possible, many ground-based observatories have joined in on the observations, allowing researchers to get data on not just how the worlds look, but also on how their temperature, chemistry, and patterns of storms change over time. Now, 33 years into its mission, Hubble has allowed us to observe 3 solar cycles and their impacts throughout the solar system. In a newly released paper in Icarus that is led by Arandi Chavez, researchers use images of Neptune taken from 1994 to 2022 by Hubble, as well as images from the ground-based Keck and Lick observatories. They use all of this data to study how much of Neptune's atmosphere contains cloud. They find that when the sun was most active in 2002 and 2015, Neptune had the largest amount of bright clouds, while the overall background brightness of Neptune's blue haze stayed constant. Cloud cover was least when the sun was at its minimum in 2007 and 2020, and the sun's particularly quiet low in 2020 was accompanied by a particularly low number of clouds on Neptune. Researchers think the increased high-energy ultraviolet radiation associated with solar max is causing the clouds to form in Neptune's upper atmosphere through what is called photochemical effects. This may not be the entire issue, however. As they point out in their press release, more work is necessary. For example, while an increase in ultraviolet sunlight could produce more clouds and haze, it could also darken them, thereby reducing Neptune's overall brightness. Storms on Neptune rising up from the deep atmosphere affect the cloud cover, but are not related to photochemically produced clouds and hence may complicate correlation studies with the solar cycle. More observations are needed, and they have JWST data now, so future years of observations will hopefully resolve what's going on. Exactly why Neptune, the farthest away from the major planets, is so affected is also curious. But this world just hasn't been studied a lot. And with no missions currently planned to visit it, science can really only advance at the pace of telescope advancements. Luckily, our ground-based telescopes are steadily getting both bigger and, inch for inch, more sensitive. This evolution, along with the changing of the Neptunian seasons, has allowed the Very Large Telescope in Chile to resolve a dark spot on Neptune for the first time. These results appear in the journal Nature with first author Patrick Irwin. According to Irwin, quote, "Since the first discovery of a dark spot, I've always wondered what these short-lived and elusive dark features are. I'm absolutely thrilled to have been able to not only make the first detection of a dark spot from the ground, but also record for the very first time a reflection spectrum of such a feature." Researchers use reflection spectra to look at what colors of light from the sun and other objects, like Neptune, absorb and reflect. This in turn allows them to estimate the chemistry associated with what they're seeing. They determined the dark spot originates in the lowest visible layer of aerosols in the Neptunian atmosphere and suspect the spot is formed either from upwelling material from deeper in the atmosphere, where they can't see, or from the melting of hydrogen sulfide ices in the atmosphere and the subsequent revealing of dark dust cores within the ice. Essentially, just like melting snow can leave a visibly dark soot on city streets, melting hydrogen sulfide ices can leave dark patches in Neptune's atmosphere. Maybe. Determining exactly which scenario it is will require additional observations. I, for one, hope our increasing understanding of just how weird Neptune is will result in the funding of a spacecraft to visit Neptune. One world that doesn't lack for visitors is Mars. It makes sense. It's not too far away. It potentially had or has life, and we can easily imagine walking on its desert surface. While I can want more Neptune missions, I also can't really say no to Mars missions. This week, we got a bunch of updates from Mars missions that are already there. The Curiosity rover, which is exploring Gale Crater, has previously sent back images showing amazing cracks in the former lake bed that it is exploring. A new paper in the journal Nature, led by William Rapin, explains that, quote, "These particular mud cracks form when wet, dry conditions occur repeatedly, perhaps seasonally. This is the first tangible evidence we've seen that the ancient climate of Mars had such regular Earth-like wet-dry cycles. But even more important is that wet-dry cycles are helpful, maybe even required for the molecular evolution that could lead to life," end quote. I fervently hope we are able to go fossil hunting on Mars in my lifetime. Sadly, Curiosity just isn't designed with that kind of science in its mission plan. Instead, this 11-year-old rover is working on climbing Mount Sharp, the central peak in Gale Crater. Over the eons, this mountain has been home to a variety of rivers, lakes, and other features. And with each gain in altitude, the rover is able to explore a different part of Mars' history. Meanwhile, over in Jezero Crater, the Ingenuity helicopter has recovered from having to make an unscheduled but safe landing. On August 3rd, it made its 54th flight and returned a breathtaking aerial view of its surroundings, which happened to get photobombed by a distant Perseverance lander. While the InSight lander now rests in peace on Mars, its data continues to tell us new stories. In a new paper in the journal Nature, led by Sébastien Lemastre, researchers report that Mars appears to be rotating about a fraction of a second slower each year. The exact cause is unknown, but it's likely related to a redistribution in the planet's mass, for instance through the growth of polar ice caps or the rebound of land once covered by glaciers. It turns out, when you cover a world in robots, cool science is the result. After a break, we're going to journey outward to look at exotic star systems. Stay tuned. There are certain fundamental questions that get people interested in astronomy. How did it all start? How will it all come to an end? Where did we come from? And there are the questions you ask if you read or watch science fiction. Questions like, can a system with 3 suns really exist? Yes, they can. It turns out that middle-sized stars like our own sun tend to form in pairs or groups. As we look out across the sky, we find more variety of star systems than our human minds had previously imagined were possible. Which brings astronomers to the question, how does that even happen? And up until now, forming stars haven't made it easy for us to figure it out. Stars form in clouds of gas and dust, and their formation is often hidden by material or obscured by the bright light of other stars. Sometimes we get lucky though, and that's just what happened to a team of observers using the Atacama Large Millimeter and Submillimeter Array, or ALMA. While observing what appeared to be a trio of forming stars, they looked for light from sulfur monoxide, a common molecule in star-forming regions that shines at the temperature of this baby star system. These observations are detailed in a new paper in the Astrophysical Journal that is led by Jung-Un Lee. By looking at how this gas is flowing into the system, they were able to figure out how gas and dust feed into these kinds of stars as they form. What's more, using these observations, they were able to test computer models to see what science matches what we see. The result is a dramatic data visualization that shows how a cloud can begin to collapse and ultimately fragment and draw in streamers of surrounding material. While we can only compare one frame of this movie with the illustration, this at least tells us we're on the right track. Hopefully, future ALMA observations of other systems will allow us to verify other frames of this model. Stars in multi-star systems don't just have complicated births, they also have complicated lives, especially when their orbits aren't circles. Binaries in highly elliptical orbits slowly dance together and fly apart over and over. In some systems, each close passage causes the system to brighten as waves of plasma rise like the tide from the stellar surfaces. These systems are called heartbeat stars because their periodic brightening looks like the pattern of a heart on an EKG. Usually, this is a tiny effect. It's easy enough to see if you look for it, but it doesn't usually trigger systems looking for novae or gravitationally lensed stars. One system, however, couldn't beat softly, but instead raged like a storm surge. First discovered in 1997, this system was found to change in brightness about 20% every 33 days for reasons that weren't initially clear. A 2019 analysis of data from the TESS mission and the All-Sky Automated Survey for Supernovae determined the system consists of 2 massive stars on elliptical orbits. Why this made their heartbeat so bright? That took a few more years and a large computer model to figure out. In a newly published paper in the journal Nature, Researcher Morgan McLeod presents the results from a new computer model that looks in detail at what is happening to the larger star's atmosphere. Coming in at 24 times the radius of the Sun, this star is a giant. When the smaller, yet still massive companion rushes by, gravitational pulls generate giant tides, just like our ocean's tides, on the surface of the star. While our ocean tides are generally measured in meters or tens of meters, this star's tides are measured in millions of kilometers. At a certain point, it is difficult to comprehend just how big numbers are. Let me see if I can break this down. There is a star with 24 times the radius of the Sun. Every 33 days, a massive tide is lifted up and rises so high that 3 suns could be stacked inside the wave. The wave is fully 20% of the star's radius. If the Earth had a tidal wave 20% of its radius, that wave would engulf all the satellites in low Earth orbit as it stretched nearly 1,300 kilometers into space. Does that give you a sense of just how big the tides rise on this star? Here on Earth, our tides are carried around and around our world by the moon, day after day, year after year. With this star system, as the smaller star orbits away, the forces that sustained the tides slip away as well. As a result, the tide crashes like a breaking wave, releasing a tremendous amount of energy. And just like a crashing ocean wave can fill the air with water droplets, the crashing plasma waves on a star can fill the region around the star with star bits. The result is a massive star that has a radius 50% larger at the equator than at the poles, in part because the crashing waves fling out material into an expanding atmosphere. I'm at the point of believing that any crazy sci-fi star system that doesn't defy physics probably actually exists somewhere out there. 3 suns, 2 moons, stellar tidal waves, all of it. It's all true. The shape of an orbit can cause all sorts of weird things to happen. For instance, in another binary system, researchers discovered a brown dwarf star nestled up to a very hot white dwarf star. Its small circular orbit has locked the brown dwarf's rotation, so the same side of the brown dwarf always faces the hot star, just like the same side of the moon always faces the Earth. While it's interesting that we only ever see one side of the moon, it doesn't have a profound impact on us or on the moon. For this brown dwarf orbiting a white dwarf, things are a bit different. White dwarf stars are typically about the mass of our sun, but only the diameter of our moon. They are the leftover cores of dead stars, and they can be extremely hot. This white dwarf is about 37,000 degrees. For comparison, our sun is 5,200 degrees Celsius. This extreme heat can have extreme effects. As the 80th Jupiter mass brown dwarf goes round and round, orbiting every 2.5 hours, it keeps the same side always facing that very hot white dwarf, which heats it like a marshmallow held next to a fire. New research published in Nature Astronomy and led by Naomi Halakon shows the brown dwarf is 8,000 degrees Celsius on its daytime side and just 2,000 degrees on its night side. That's a difference between day and night of 6,000 degrees. Normally, brown dwarfs are extremely cool and very hard to find. This one, because it is superheated and physically a lot larger than the moon-sized white dwarf, well, it's actually relatively easy to see. I guess the moral of the story is, if you're a brown dwarf and want to get noticed, find a hot, smaller star to put you under its spotlight. After the break, it all goes fuzzy as we look at gravitational lensing and its power to blurrily show us the otherwise invisible parts of our universe. Later on, we bring you the latest news from the launch pad. Stay tuned. In this week's Closer Look, we take a look at dark matter. You often hear folks saying our universe is weird and wonderful. An equally true but less articulated fact is our universe is frustrating and seems to play coy about its nature. In 1933, Fritz Zwicky observed a discrepancy between how much matter appears to be in galaxy clusters based on observed matter and based on the motions of that matter. The motions seemed to indicate some unseen component was present. The same kind of discrepancy was later seen by Vera Rubin in the 1970s as she studied the rotation of galaxies. She found that the outskirts of our own galaxy and others rotate faster than expected based on the stars, gas, and dust we're able to observe. Over the decades, generations of researchers have tried to explain this discrepancy as either a misunderstanding in how gravity works at large distances, or as evidence of a hidden component of nature that just doesn't interact with light. While we can't completely rule out the possibility that gravity has some extra term we have yet to discover, we can say with certainty that our universe is filled with patchy clouds of particles that neither reflect nor absorb light, but do bend light with their gravity. Called dark matter, we now know this mysterious stuff makes up about a quarter of the universe and influences everything from how the first galaxies formed to how modern-day galaxies spin and fall apart after collisions. Mapping the distribution of stuff we can't see directly has been a challenge. But it turns out it's more of a tedious problem than a difficult problem. As we look out through space, the light from galaxies at different distances has to pass through and near clouds of dark matter as it journeys toward us. If there was no dark matter, we could look out and see that at any given distance, the shapes of all the galaxies would average out to a circle. This is because galaxies are equally likely to be oriented in any direction, and by looking at enough systems, that randomness results in a nice friendly blob of light. Dark matter, however, can change the perceived shape of things by causing all the galaxies whose light it affects to appear distorted in the same way. This means that when we look at hundreds of galaxies in one direction, we might see them average out to a teardrop, while in another direction they average to look like an amoeba. By looking at galaxies at a variety of distances and seeing how light is distorted in more and more complex ways, we can even get at the three-dimensional structure of dark matter. Essentially, by looking at nearish systems, we can see galaxies that are distorted by only the dark matter between us and those galaxies. When we look at more distant systems, we know they should be distorted the same way as those nearish systems, and also distorted by the dark matter between them and the second set of galaxies. As the resolution of our telescopes allows, we can look further and further back and build up an increasingly complex map of dark matter that is based strictly on the way its gravity distorts light. This kind of measurement was first accomplished by the Cosmos team and published in 2007, and has since been replicated at a variety of different scales to measure everything from the distribution of dark matter in colliding galaxies to the massive galaxy clusters to, well, earlier this year, the Atacama Cosmology Telescope even released a map of the distribution of dark matter over roughly a quarter of the sky by looking at how light from the cosmic microwave background has been shifted by this invisible matter's gravity. These surveys have left us with an overall impression that dark matter is made of a particle that doesn't interact strongly with itself or other particles, kind of like a neutrino, and that it will clump up, but not necessarily into very dense amounts. It could be one specific kind of particle, or a variety of different particles that all share the same ability to not interact with light. What we haven't known until now is how dark matter piles up at the smallest scales, by which I mean galaxy and star-sized scales. But that is starting to change. A few weeks ago, we reported on strange objects seen in the early universe that are either giant fluffy clouds of dark matter that are forming stars, or the cores of galaxies behaving in ways we haven't previously seen. Now, researchers have published results on the distribution of dark matter within a single galaxy by looking at how it distorted light from a distant quasar. The foreground galaxy is truly massive, and its gravity has bent light intended for other parts of the universe so that they travel toward us instead. Because the galaxy isn't a perfect sphere and the alignment with the distant quasar isn't a perfect line, we actually see three different distorted views of the quasar. Each image is distorted by the specific distribution of matter it encountered, and this multiple image set gives us three different measurements of the galaxy's mass, in addition to the measurement we get from looking directly at the galaxy's distribution of luminous stars and gas. This kind of a multi-lensed study isn't unusual, but what makes this one a little bit different is the researchers use the Atacama Large Millimeter and Submillimeter Array instead of more typical telescopes that look at light in optical or infrared colors of light. Working in these near radio colors, ALMA is able to see details smaller than can be seen with any other single modern observatory. Its high resolution allows researchers to make out slight differences between each of the different lensed images, differences that can't be explained by the distribution of visible matter in the galaxy. This implies that dark matter in the galaxy is responsible for these differences, and it tells us that dark matter can clump up on scales as small as 30,000 light years across. These results are published in the Astrophysical Journal in a new paper with lead author Keiki Taro Anoi. This is the first time variations in dark matter have been measured on these kinds of smaller scales. Now the question becomes, on just how small a scale can we see dark matter piling up? A new paper in Physics Review Letters offers a tantalizing new way to go looking for dark matter. Led by Salanja Bhattacharya, this paper points out that it may be possible for dark matter particles to collect over time in the cores of neutron stars and eventually turn them into black holes. They postulate that dark matter particles might initially compress themselves into microscopic black holes as they interact with other particles in the neutron star. And then over time, they can consume the surrounding neutron star until all the mass is a new, smaller than otherwise predicted black hole. While we can't see black holes directly since they don't give off light, we can detect the gravitational waves they release when they merge with other objects. This team postulates that some of the gravitational wave detectors here on Earth, like LIGO, Virgo, and KEGRA, may be able to detect these mergers. The trick will be in knowing if dark matter created these systems, or if they are the result of primordial black holes from the formation of the universe wandering into binary stars. If Stephen Hawking's theories were right, any primordial microscopic black holes should have evaporated by now. So I guess we're going to need to understand black hole evaporation before we can understand exactly what it is we might one day see. When and if these kinds of observations are made, we'll bring them to you right here on Escape Velocity Space News. For now, we need to take another break. When we come back, I'll be welcoming on Eric Mattis for this week's Tales from the Launchpad. Stay tuned. Lately, it seems like everyone has been launching rockets, and we have a packed rocket segment tonight. I'm pleased to welcome on aerospace correspondent Eric Mattis to let us know all about what's gone up, and in one case, what came back down a bit faster than intended. Hey, Eric.
Hi, Pamela. We're starting off this new season with the first time we've ever had 3 lunar landers to talk about in 1 week, plus the usual Starlinks and Chinese launches, and 4 more humans ride into space. So many things happened between the last show and this one that we only have time to cover the highlights. I had a whole lot to say about Luna 25, How it showed the Russian space program still has it after almost 50 years of no lunar landings and two consecutive failures to even leave low Earth orbit in 30 years of the post Soviet program. Luna 25 did successfully leave Earth orbit, but then deorbited itself into the lunar surface at 5,000 kilometers per hour due to a programming error. Landing on the moon is hard. Instead, we're going to talk about the lunar lander that actually succeeded in landing on the moon, India's Chandrayaan 3. Chandrayaan 3 is India's second attempt to put a lander on the moon. As we told you last season, the Indian Space Research Organization, or ISRO, made major changes to the lander's structure and, more importantly, its flight software since the previous attempt in 2019 that was unsuccessful. In brief, they made the leg stiffer, added a bigger fuel tank, and taught it to be more flexible in choosing its landing site and reacting to off nominal situations. This time, it was successful, touching down at the lunar South Pole on August 23rd. As the lander and rover were not designed to survive the extremely cold temperatures of the lunar night, this marked the start of a frenetic 2 weeks of activity. There were several discoveries during these 2 weeks. The mission discovered that the lunar regolith doesn't conduct heat very well, with temperatures dropping to freezing only 7 centimeters below the surface. This is a good sign for the existence of ice closer to the South Pole, an important resource for crewed missions if they want to stay for long periods of time. Spectrometers on the rover revealed that the lunar rocks around the landing site have a much higher concentration of sulfur compared to the other rocks on the moon. The Langmuir probe on the lander made the first measurements of plasmas in the lunar environment around the lander on the South Pole. Initial results suggest that the plasma near the surface of the moon is relatively sparse. However, the results are from early in the lunar day, so there could be changes as the lunar day progresses. Once more data has been analyzed, scientists will have a better understanding of how the lunar environment changes over the course of the lunar day. With the approaching lunar night, on September 4th, Chandrayaan 3's lander and rover were oriented to face where the sun will be when it returns on September 22nd, before they are powered down. Time will tell whether it survived the darkness to conduct more experiments. And finally, on September 6th at 2342 UTC, Japan launched an H2A202 rocket carrying JAXA's Smart Lander for Investigating the Moon, or SLIM, and the XRISM telescope. The first payload is SLIM, or Smart Lander for Investigating the Moon. It's a fairly small lander, weighing 730 kilograms when fully fueled, and measuring about 3 meters wide and 2 meters tall. The primary purpose of SLIM is to demonstrate sub 100-meter landing accuracy to reach a specific target on the lunar surface. Typical lander accuracy is measured in the kilometer to dozen kilometer level, so landing within 100 meters will be a significant improvement in accuracy. JAXA wants this ability to study individual rocks up close and find water ice on the lunar poles. Since the ice is found in only relatively small areas, it will require a high precision landing. SLIM has a powerful computer vision system to identify the targeted landing site from orbit and then guide the lander down to the exact spot. The target for the mission is on a crater wall with about a 15-degree slope. This requires a unique landing sequence. The vehicle will touch down on its side, with one set of legs first, and then settle down on the second set. To save money, the SLIM lander is launching with another payload, the X-ray Imaging and Spectroscopy mission. Pronounced XRISM, it's a very interesting payload in its own right, an X-ray telescope with two instruments that will study galaxy clusters, black holes, and spacetime. Its imaging payload is inside a liquid helium cryocooler, which takes its sensor down to half a degree above absolute zero. One of the instruments is a collaboration with NASA, and the other is with ESA. SLIM has a lot of clever technology to keep the size down to fit on the rideshare. The primary lander structure is its fuel tank, which combines the propellant and oxidizer in one tank. Its solar panels are very thin and flexible, and some are attached with Velcro instead of heavier metal fasteners. It has a single computer that does spacecraft tasks and processes the data from scientific instruments, saving weight. Its battery is lithium ion within a carbon fiber reinforced plastic shell to save weight. Because of its small size, the SLIM lander only has a single instrument, a multispectral camera. It will also deploy a pair of small probes just before landing to take pictures of the lander on the surface. SLIM also has a retroreflector provided by NASA like Chandrayaan 3. Both missions, CRISM and SLIM, were confirmed in contact and power positive in a post-launch press conference. We keep track of orbital launches by launch site, also called spacewalk. According to RocketLaunch.live, so far this year, the USA has had 68 launches, China 41, India 7, Kazakhstan and Russia each have had 6, New Zealand 5, Japan 3, French Guiana and North Korea each have had 2, and Israel, South Korea, and the United Kingdom each have had 1. Of these 143 launches, there have been 6 failures, reminding us that space is hard.
Thanks, Eric. Before we go, I want to go back to Neptune again and let you know about one cool anniversary that is coming up. On September 23rd, we'll mark the 177th anniversary of Johann Galilei discovering Neptune. Working in the years before the invention of photography, Galilei relied on his own eyes and maps to look for things that were moving among the stars. Luckily, he didn't have to search the entire sky. The odd shape of Uranus's orbit had led astronomers to speculate that another giant world should be in the outer solar system. Mathematician Urbain Le Verrier had predicted where Neptune should be, and when Galilei pointed the Berlin Observatory telescope at that location, he found his planet. Remarkably, just 17 days later, British astronomer William Lassell spotted Neptune's massive moon Triton, which is 40% larger than Pluto and considered to be a captured Kuiper Belt object. Since its discovery, Neptune has completed just over one orbit around the Sun, and that orbit doesn't explain the oddities of Uranus's orbit. We now understand that things are even more complicated than previously thought, and maybe there just might be one more world out there waiting to be found, although it also won't explain Uranus's orbits. Sometimes weird and wonderful stuff just happens. That's it for tonight. We'll be back next week with updates on the OSIRIS-REx mission and a look ahead to October's annular eclipse. Good night, and remember to look up.